In this video, we are going to talk about one-way or single-factor ANOVA. And ANOVA is what is called analysis of variance. And it's sort of a cool concept in that we can actually decompose different populations' dispersions to test to see whether those same populations have the same mean. So I can use the variance to test the mean, to test to see whether the mean differences are to test to see whether the means are different from each other. And so this is useful when we want to see whether multiple means are equal to the same number, say more than two means. So if we had just two means, we might consider just using a two population test statistic. But if we have more than two means, we might not consider doing that. So for example, let's say I wanted to test to see whether different routes to Atlanta from Carrollton have the same mean. Well, there are a few different ways that I could go to from Carrollton to Atlanta. I can go up 119 to Temple and take Interstate 20 to Atlanta. I can take US 78 from Villa Rica through Douglasville into Atlanta, kind of like a Bankhead Highway. I can go through the woods past the fancy house with the water slide on 166, or I could take 16 down to Noonan and fly up on 85. I can test to see whether these have the same mean. So intuitively, in this example, I don't think it takes the same amount of time to go these routes, but if I were to adopt a two-population approach, I might have some difficulty gleaning that. So for example, let's suppose I made a comparison between taking Interstate 20 and going to Noonan and taking Interstate 85. Clearly I'm going to reject the null in that instance. But then let's say I were to subset State Route 166 through the woods, kind of the back roads to Atlanta Airport, with US 78 through Douglasville. Well, actually, it might take the same amount of time either route to get to Atlanta, so I wouldn't reject the null. And so I end up with this set of circumstances where for some of the groups I reject the null, and for other groups I don't reject the null, and it's difficult to know what to make of all of it. So which two population test actually represents a comparison of all the means? And the answer is none of them, because we're only comparing two of the perhaps k different routes to get to Atlanta. And statistically, we're going to reject the null at some point. So even if we're comparing things that are relatively close together, like something like drive-through times at local fast food places, well, one of them is the slowest, and one of them is the fastest. And if I can put the fast food restaurants in order from slow to fast and compare the slowest to the fastest, I stand a reasonable chance of rejecting the null in a two-population environment. But if I compare the ones in the middle, I don't. And this is not to say that they do or do not have the same mean, but what it is saying is that when I put numbers in order from small to large, if I compare the smallest to the largest, there may be a statistical gap there. And if I compare the ones in the middle, there may not be. And so we want to try to avoid this approach of a two-population test statistic. And what we want to do is minimize what's called type 1 error. We want to avoid rejecting the null in instances when we have no statistical justification to do so. So the point about doing a hypothesis test at a 90, a 95, or a 99% level is that we shove that type 1 error down to 10%, 5%, and 1% respectively. However, when we do a bunch of hypothesis tests in a row, at some point we will commit type 1 error. And our goal is to change this problem to just doing one hypothesis test. So we do what's called ANOVA. The goal of ANOVA, the null hypothesis, is that the different K populations have the same mean. So the mean of group 1, and you could think of this as taking 20 to Atlanta, is the same as the mean of group 2, which you consider as being taking 85 to Atlanta, which you consider the same as group 3, 166, group 4, maybe I go through Villa Rica, group 5, going down through Noonan, etc., etc. The null is that they are equal. The alternative is that they're not equal. Okay, and we cannot do a one-sided hypothesis in this environment. I can't rank them from small to large. All I can do is say they're equal or not equal. So I combine all possible comparisons into one comparison. And so if they're all equal, then one number could represent the mean for all the population. So there's one physical time that it could take to Atlanta that could plausibly be the same for all the 5 routes. That's what the null is saying, and the alternative is saying that that's not the case. We make some assumptions when we do ANOVA. The first assumption is that we have normally distributed populations, which is fairly realistic. The second is that the populations have the same standard deviation. Could be worrisome. We could look at doing an F-test to do this, comparing the variances, do a two-sided test there. We could potentially corroborate this. And the third is that the populations are independent, which I think is fairly realistic. So the concept behind ANOVA, I think, is really elegant. We calculate one mean for all of our data, and we examine how far away our data are from this number. So in the null, if the different populations are equal, then one number represents them all. So what we're going to do is we're going to calculate that sample number, that's the grand mean, and we're just going to see how far away our data are from the number. All of the data from all of the populations. So we sample all times from all of these different routes to Atlanta, and we measure how far away they are from that number. And then we calculate within category means and examine how far the numbers in the category are from their means. And what this means is that I'll actually calculate an estimate for the mean of group 1, the mean of group 2, the mean of group 3, etc. And those are going to be category means. And then I'm going to measure how far observations are from the category mean. So on the first bullet point, I combine all the data together, take the average, and see how far each data point is from that mean. And that's, think of it as within the entire sample, kind of something like a standard deviation. And then I do it just category by category. And the cool idea here is that if the data are really far away from the overall mean, but they're not very far from their categories, that means that they're dispersed compared to the overall mean. They're far away, but they're not far away from their own group, which means we have one group that's far away to the left, one group that's far away to the right, and it starts to tear at the idea that these groups have the same mean because they're close to each other, but they're far from the overall mean. Okay, so conceptually, let me give you an example of this. Let's look at family spending at local pizza places. And we have 3 bell curves that are of similar width. The orange one corresponds to Pizza Hut, the red one corresponds to Domino's, and the blue one corresponds to Johnny's over by Walmart. And you can see that the means are different. Pizza Hut's mean is 25, Domino's is 26.5, Johnny's is 27, but you also see that right in this area here, the blue, the red, and the orange have a lot of overlap. So it's possible in this picture that I could throw out the 25, the 26.5, and the 27 and represent them all with, say, 26. In this case, the null is more plausible. The null is more plausible. If I were to test the hypothesis that the mean of Pizza Hut is equal to the mean of Domino's is equal to the mean of Johnny's, I might not reject the null. And just visually, you would think that, hey, what if I just threw out these 3 bell curves and represented all spending at local pizza places with one bell curve where the mean is 26? Would that be reasonable? And in this instance, it certainly might be. Let's take a look at another example. Going back to the fast food, we look at spending at Crystal, which is no more, Chick-fil-A, which is in orange, and Moe's, Southwest Grill. And you can see here that all of a sudden there's not very much overlap between Crystal and Moe's. So when you go to Crystal and you look at your receipt, there aren't many instances where people are ordering enough food at Crystal to have a bill that is similar to what they get at Moe's. And so we certainly wouldn't think that Crystal and Moe's have the same standard deviation, but if you take a look at the overlap between Crystal and Chick-fil-A, we might, or sorry, the same mean, but if you look at the overlap between Crystal and Chick-fil-A, you might also think they don't have the same mean either. And in this instance, if we're testing a null which says that Crystal and Chick-fil-A and Moe's have the same mean, just based on the picture, it sure doesn't look like that's plausible based on what we see here. And so with analysis of variance, the idea is that we're going to construct an F-stat to kind of reproduce this picture with one additional graph where we have an example of the whole bell curve. And we're just trying to see if it's more reasonable to, in this instance, I might be better served representing all three of these with one bell curve, but in this picture I certainly wouldn't be. The null represents something like one bell curve. The alternative represents multiple bell curves. Okay, so ANOVA is a fairly intricate process, and it does comprise a bulk of exam 2. So around 40% of exam 2 will be using single factor ANOVA, which is what we're doing today. So if we go back to these slides here where we're trying to conceptualize what ANOVA is doing, we're going to calculate a mean for all the data and examine how far away our data are from this number. So we're going to try to represent the null in some way, and then we're going to do within category means and examine how far the numbers are from the category means, and that's going to give us some info about the alternative. So the first step in ANOVA is we calculate the mean of all the data, and that's X bar grand is the grand mean. So if I have 3 restaurants, I take all the data from all 3 restaurants, I average it together. Then I measure how far the data are from the overall mean, I square it, and I add it together. And that's called the sum of squares total. So I take each data point, subtract the overall mean, and square it, then I add it together. And you may think of this as being like a measure of variance from all data from the overall mean. So it functions similarly to the overall variance, with the exception of we're not dividing by n-1 here. We then do the same thing for each category. So I calculate as many means as there are categories. So if I have different columns of data for each category, I just do a column mean. I measure within category distances. So I take each data point, I subtract the category mean and square it. So I only do within categories, so I don't mix and match. So I don't take, for example, Crystal data and subtract the Moe's category mean. I just do Crystal minus Crystal, Chick-fil-A observation minus Chick-fil-A mean, etc. here. We have a term for this. It's called the sum of squared errors, but you could think of this as just kind of loosely piecing together the individual dispersion from the blue, adding it to the yellow dispersion, and adding it to the orange dispersion, and adding it to the red. This is called the sum of squared errors. The variation with which we test the hypothesis comes from the difference between the total and the errors. So I take the sum of squared total and I subtract the sum of squared errors, and what's left over is what's called the sum of squared treatments. Okay, so this is quite a lot of work. We're going to work through it here in an example, but this is where the analysis of the variance comes in. Then we need to construct a test statistic with this an analyzed data. So we take the test statistic as follows. We use the sum of squared treatment, which is the total. That's each observation minus the overall mean. minus the errors, that's each observation minus the category means, and we divide by the number of categories minus 1. So the sum of squared treatment here divided by k. K is the number of categories. In each of these examples, we had 3. Okay. Categories minus 1. So think of this as being sort of the place where we do our deconstruction of the variance. And this is called the mean squared treatment, MST. It should be MST. We then do the same thing with the errors. We take the sum of squared errors and divide by n. That's the number of observations minus k. That's the number of categories. This is called the mean squared error. The f-stat, you take the mean squared treatment, divide by the mean squared error. So lots of steps. Both bullet points tell us all the steps. Let's go over an example. And here we're just looking at Likert-style ratings for Wendy's in 3 West Georgia locations. So there's a Wendy's in Bremen, there's one in Carrollton, and there's one in Bowdoin. And I want to see if people view these Wendy's with the same degree of favorability. So 1, you hate Wendy's. 5, Wendy's is amazing. The null, the mean of the Bremen is equal to the mean of the Carrollton is equal to the mean of Bowdoin. And what this means is that I could replace all 3 sets of ratings with 1 rating. The alternative is that they're not equal. Okay, so this null and alternative sets up the same as what we did here, and this is the only type of null and alternative that we'll be testing with ANOVA. Okay, so we have collected 4 ratings from Bremen. One person gave it a 4, another gave it a 2, and 2 others gave it 3s. We've collected 5 ratings from Carrollton, which has received 1 4 and 4 5s. We collected 5 ratings from Bowdoin as well. We've received 2 4s, 1 3, an additional 4, and a 5. What I want to point out in this example is that we actually don't need the same number of observations for Bremen, Carrollton, and Bowdoin. That is not necessary for ANOVA, just like it wasn't necessary for 2 population. Okay, so now let's start looking at the steps. In order to do these sum of squares, I need category means and overall means. So the category means, I add up the Bremen. I have 4 plus 2 plus 3 plus 3. That's 12 divided by 4. The average Bremen rating is 3. I do the same thing for Carrollton. 4 plus 5 plus 5 plus 5 plus 5. That's 24 divided by 5, 4.8. I do the same thing for Bowdoin. Add them up. You get 20 divided by 5 ratings. That's 4. So the category means are 3, 4.8, and 4. Then if we take these little subtotals here, so I have 12 plus 24 plus 20, that's 56, divided by 14, that is 4. Okay, so the overall mean is 4, which is the same as Bowdoin, but Carrollton is higher and Bremen is lower. And we want to say if we can rule out, based on this, that they have the same mean. Okay, let's take a look at the sum of squared errors. Here were the category means, 3, 4.8, and 4. I take each data point, I subtract the category mean, and I square it. So I do it for Bremen. 4 is the first data point, the category mean is 3, I square it, I get 1. 2 minus 3 is negative 1, squared, I get 1. 3 minus 3 is 0, 3 minus 3 is 0. 1 plus 1 gives me 2. For Carrollton, I have 4 minus 4.8, that's minus 0.8, squared, 0.64. Then I have 5 minus 4.8, that is 0.2, squared, 0.04. Do this for all the observations here, and you get a 0.84. Now for Bowdoin, I have 4 minus 4, which is the category mean for Bowdoin, squared, 0. Next observation here is also 4, minus the mean of 4, still 0. Then I have 3 minus 4, that's negative 1, squared, 1. Total of 2. So I have 2 plus 0.84 plus 2, that's 4.84. That's my sum of squared errors. The overall mean is 4. Okay, so I repeat the same process, but instead of having different means here, 3, 4.8, and 4, I just have 4 everywhere. Okay, and you can actually see that the Bowdoin calculation is exactly the same, but Carrollton and Bremen go up a little bit. The sum of squares total is 12. the F-stat. I need to make the sum of squared treatment. I take the sum of squares total, subtract the sum of squared error. I have 12, that was the sum of squares total, minus 4.84, that's the sum of squared errors. I get 7.16. The mean squared treatment is 3.58. K is the number of categories. I have 3 different Wendy's. Minus 1, degree of freedom, 3.58. Sum of squared errors, 4.84. Divided by n observations minus 3 categories, we have 0.44. The F-stat, take 3.58 divided by 4.44, we have 8.14. Okay, how do we use the F-table for ANOVA? How do we use it for ANOVA? Let me show you on the F-table. We are going to use alpha equal 0.05. That was what we used for 90% test with equality of variance. Here it's interpreted as 95% because the ANOVA statistic can be less than 1. Okay, so let's go back to the slides. K minus 1 is the column. K minus 1 is the column. So I go to column 2. Column 2. N minus K is the row. 14 minus 3, row 11. The critical value is 3.98. 3.98, which is smaller than 8.14. I do reject the null. Intuitively, you might think I reject the null because it seems like the Carrollton Wendy's has improvement over the Bremen Wendy's. Now, I can actually do this in Excel, and let me show you how to do it in Excel. Okay. So this is ANOVA within Excel. Give myself a little bit of room to type. Let's go up. I have Bremen. I have Carrollton. I have Bowden. Here are my data for 2, 3, and 3. For Carrollton, I had 4 and a bunch of 5s. And for Bowden, I had these data. Now here are the category means. You just take the average. Those are our category means. The overall mean is the average of these here. Now, I can use Excel to find the sum of squared errors. And I'm just going to merge and center here. I take each data point. I subtract the category mean. I'm going to use a cell reference here. $7. I'm going to lock in the row, and I'm going to square it. I copy it all the way down. I delete when I have a blank cell. You add it up. Actually get 4.8, not 4.84. So my F-stat will be a little bit, it'll be a little bit larger even than this. It should be 4.7, 7.2 is the MST. MSC is 4.8. Okay, so this is my mean squared error. The sum of squares total. Do the same thing. Take each data point, they start in A2, minus the overall mean, which is 4, and you square it. And I delete when I don't have any data. Okay, the sum of squares treatment. I take the sum of squares total, subtract the sum of squared errors. Mean squared treatment. Take the sum of squared treatment, divide by categories minus 1. Mean squared error. Take the sum of squared errors divided by n observations minus 3 categories. The f-stat. Take the mean squared treatment, divide by the mean squared error. I can even look up an f critical value. I would go to f.dist. And actually, instead of using f.dist, you can use f inverse. Probability, degrees of freedom 2. Let's see if we do 0.95. There's our critical value, 95%. Now, what I want to point out to you, and this is important, is that Excel will actually do this for you. If you go to the data analysis, ANOVA, single factor, you go to your data, just click on all of it, labels in the first row, hit OK. Excel calculated all of this for us. Here's our f-stat, mean squared treatment, mean squared error, sum of squares treatment, sum of squared error, sum of squares total, our degrees of freedom. Excel does this for us. Okay, so we will have another example of single factor ANOVA, but I want to introduce the topic today. What we're testing to see is if more than 2 populations have the same mean.